Bueno, buenos días, bienvenidos a este coloquio extraordinario. Tenemos con el doctor Hanstorp de la Universidad de Gotemburgo en Suecia y voy a cambiar inglés para decirlo. Welcome to this seminar colloquium. Today we have Professor Hanstorp from the University of Gothenburg, expert in negative ions and many other fields. He has, at least to my knowledge, like 4 or 5 projects always running in parallel. He will talk about it in that one. Introduction, I guess, but you will hear that. Of course, for some of you that don't know him, he is, together with Antonio and me, Antonio and Alex. Some of you might remember Alex Black, who used to be here. He was working at Berkeley. How we got in contact, and that's how I started this exchange program with the University of Gothenburg, in and the University of Gothenburg. Many of you have hosted students or some other professors that have come here, and also he has 2 opening positions for this exchange program and also for a PhD. At the end, you are welcome to talk to him if you have questions about scholarships or positions. He used to be Ingvar Lindgren student. For some of you that might have worked on quantum mechanics and theory, he was one of the big professors of Sweden. So although he started in a theory group, his experimental is 100%. So we will see that in the talks. So there is, I didn't present it, but there is a nice story of how that group came out to be in the 60s and 70s. Anyway, the exchange program we had 20 students plus exchange in the last 10 years. There was many other professors that have come and go. So I wouldn't take more time of the introduction. It's very good that have you here after 10 years of rest. And today he will talk to us in Spanish. Iones negativos, frágiles sistemas cuánticos. Thank you very much, Dak, for accepting it here.
Now, okay. And this is how I started to come into science. When I was 6 years old, my parents gave me a globe, and it's this very globe. And I watched this. Like I say, there's no globe on the earth that has been watched so much as this one. I looked for the highest mountains, longest rivers, names, colors, and etc. And then I started to think about why it's round, or why those people, straight up, why don't they fall off? And so my intention was to become a geographer, but for various reasons, I then ended up in physics instead. And of course, then since I wanted to become a geographer, I start here. So just to point out where I'm from, if you want to go to Sweden, go down to the Gulf of Mexico, and then get on a raft, sit and wait for some months, and with a probability of 4, you will end up where I live up here, and in Gothenburg. And so Gothenburg is the industrial city of Sweden on the west coast. And if you come to Sweden, you would Gothenburg on the raft from Mexico. You will first see the archipelago, and then you will come under the big bridge, and then into this city, which is built on the mouth of the biggest river in Scandinavia, exiting here. About 500,000 people, so it's like the size of Cuernavaca. And I just wanted to show this map. I mean, I'm not sponsored by NSF, so I can still use the proper name of the Gulf of Mexico. Okay. So in Sweden, just to say, there is a population of 10 million people. The area is about a quarter of Mexico. It's very up in the north. And if you look on this map now, green means forest. Basically, pine forests like this. You see the covering most of the country. There are some small yellow spots where we have agriculture. And up in the mountains, we have a mountain ridge. It's a very old mountain ridge that has been polished by the polar ice. because everything was covered by the polarized 5,000 years ago. Okay, so the reason I come here is that I talked. We have a collaboration between UNAM and University of Gothenburg called the Linus Palme Exchange Program. And just to see the coincidences things, the reason that I'm here is because of Alex Aguilar. We worked at ALS, synchrotron radiation, and we had a good collaboration, and I wanted to find funding. I found this program, Linus Palme program, and Alex, as Remy said, he's an alumni from here, but he was in the States, and this program did not allow to apply for collaboration between Sweden and US. But then he said, okay, why not start with Mexico instead? So he contacted his old colleague, Antonio Juarez. And then we applied for this funding. And then we had run this program for 10 years. And then after some time, Remigo took over the responsibility. And just to point out here, Linnaeus Palme program, Carl von Linnaeus is maybe the most famous Swedish scientist. He was basically the founder of systematic botany. He was on the verge doing what Darwin did, but he just mapped out things. He's like Tycho Brahe in biology. And he, sorry? Yeah. Sorry? Yeah. And he sent out a lot of his students over the globe to go and watch and bring samples back to Sweden. And he called his students his disciples. And as far as I know, there's two people that has used the word disciples, and it's Jesus and Linnaeus. So just to see what he thought about himself. The other person is Olof Palme, who was our prime minister in the 60s and 70s. And he had a lot of connections with the southern hemisphere. And actually, he visited Mexico in 1984, and he brought a lot of people from southern part of the globe into Sweden to study and start collaborations. So this program is called Linnaeus Palme, basically meaning that the Linnaeus student goes from Sweden out, and the Palme student goes from somewhere else to Sweden. And as I said, we have run this very successful program. A number of UNAM professors has visited us, some of them multiple times. And a number of Gothenburg University professors has visited UNAM. And we have had about 20 UNAM students coming to do master projects in Gothenburg. And we have had about 10 Gothenburg students coming here to UNAM. It's been very successful. I'm very happy with this. The Mexican students that have come have really contributed, been very talented. And just to show you this, the success of their studies, the red dot here means that one of those 20 ended up doing PhD projects in Europe, with the latest one starting up in London in just this month. So, and here you can see that it's slightly different. This is about the same time of the year in Sweden. Now, due to, this is Claudia, she just got some snow in her back here, so she's kind of bending over. Unfortunately, there's not so much to this anymore because of the climate change. There's very little of the snow in Gothenburg. And since we're very far up north, but as we say, the Gulf Stream brings the warm water up to us to make the life livable there. So that was kind of an introduction. Now I will just introduce my research fields, what I work with. And the topic of today is my main topic, and the negative ions. But then I just would like to mention the other projects, not the least because for master students who want to make a project, all the other ones are also available. And one thing I work with quite a lot is what's called optical manipulation. Well, and optical levitation, and I do like this and start the video. What you see here is a laser beam directed up here. This is about 3 centimeters. And what you see there is a small oil drop that is balancing on the laser beam. So the optical forces keeps it in position. This was a master project, and actually the first version of this, we used bicycle lubrication oil and sprayed and allowed it to fall down and hit the laser beam and trap it. Here we have done, this is a large research project. Javier, who is a PhD student coming from Mexico, is now defending his thesis on this topic, where he studied whispering gallery modes. We have used it to measure collisions between droplets. We use it to demonstrate how we can see with your eye how one electron is removed from the droplet. So that could be another talk, but then the next topic I work with is basically called femtosecond spectroscopy. So we study, and this is clearly just applications. What you see here is a droplet of a biofuel. And the research question here is the following. If you have a diesel engine, it has been over years developed very, very nicely to make a very efficient combustion. If you now want to change that to biofuel, then the biofuel has different properties in viscosity and forces, so it doesn't work as efficiently. So we started a program, it was a postdoc of mine, who started this, to study the details of when an oil drop of biofuel is atomized, going into pieces in the combustion. And what I will show you now here, this droplet here is like 0.5 millimeter in size, and it's held in an acoustic trap this time. And then we focus a femtosecond laser beam into the center of the droplet. You see as the white spot. And go. That works. Yeah, no, it should work. Let's see now. I'll do it here, and then go back to the. Here you can now see how you make a small air bubble in the middle. It expands. And we now study this with high-speed cameras in two directions, basically to model the breakup of this molecule. And also in the theme of femtosecond spectroscopy, our latest project is about cancer research. There was a professor who's a specialist, world-leading researcher in leukemia. And leukemia is the cancer blood cells. They want to take inside of, they have a mice that have leukemia. They want to take the bone of the mice and cut it so they can do all the optics and analytics in biotechnology on the surface. But if you take a razor blade and cut, you will squeeze it. If you take a normal laser, you will heat it and burn the cells. But we're using a femtosecond laser and basically cut it, slice it like a loaf bread. And we're now going to do this and basically slice it up and put it on the microscope so the microbiologist can then basically build up the three-dimensional structure of the cells and do all the biotechnology tools for that. My final topic that I will present is about physics education research. And this came out during the pandemic. I mean, I do a lot of things, basically how you scientifically can develop how you teach physics. And I just show one example here. And this is when, during the pandemic, when the students came in, the first year students, they were not allowed to come to the university, sitting in their homes, having no social contacts. So I was contacted by the head of studies and saying, can you find out if physics exercise lab work that is compliant with the rules of the COVID? Basically saying it has to be outdoors and you have to be separated. And we should do this physics lab. And my idea then, and then since I'm out of the mood, I can expand this here. So to do this, I rented a football field. I bought a drone, and on this field, about here, I put out two loudspeakers. And then we asked the students, close your eyes, walk around, and position yourself on the spot where you have the highest volume. They just walk around randomly, and after some time, we tell them to stop. And if I just jump forward a little bit here. This point, now you start able to see like the forming lines, it corresponds to the lines where you see the maximum intensity. Of course, I'm ashamed because I gave the instructions. We saw the video after, and I'm ashamed that I gave the instruction, find the maximum, because as a mentalist, you should have known that it's much better to look for the minimum. It's much easier. So we have redone this afterwards, and actually we did this. And in Gothenburg, we have something called the Science Festival for kids. So we actually did this on the big football stadium that seats 50,000 people, and we were allowed to do the same thing in that area with 400 kids on the ground. With the results that you see that, so this is actually the first year's physics students. And like I said, the random noise is much larger if you have 11-year-old kids being the people walking around. So it was not as nice lines we observed there. Well, that's a okay. So with that, I have now kind of reviewed. So that was kind of my overview of what my research field, and I go to the topic of today, negative ions. And then I usually start my talks by showing this slide. Are negative ions good for you? This is from the New Scientist in old paper. The question here is it important to have in the atmosphere? Does negative ions affect you or not? Because of course in the air, there are ions, there are charged particles. And the question is, and this is actually people making money of this because they sell ionizers that you should buy and put in your house because then you can increase the amount of negative ions. The question is if that is real or not, because as I will show you in this talk, it's kind of difficult to detect those negative ions. But I leave this, I will come back to this slide later. So, as Remy said, I am absolutely an experimentalist, but at least I want to have an understanding of my view of things. So now I will give you my view as an experimentalist on the properties of negative ions. Therefore, I think about an atomic system. So let's say that I take the sodium atom. You have 11 protons and 11 electrons. Then I take the valence electrons and move it far away. Then, of course, I will have net plus charge here, minus here. I have a Coulomb force that pulls this keeps the system together. Now, as this electron now is approaching, you will start to polarize the electron cloud. So the other electrons will move to the other side. I would say this scales, of course, as the Coulomb potential 1 over R. Here you will get a 1 over R to the 4th potential. And if you go even further, the electron will go into the electron cloud of the other, and you will have a potential that decays as the decay of the potential, which is 1 over the E to the R. This holds for any atoms, molecules, positive ions. And of course, this is the leading strongest term that gives you your Rydberg states in the atmosphere. But now, if you talk about the negative ion, of course, this one disappears. If I now make sodium minus, I will have the neutral sodium and an electron here. So the obvious question is, why does this really want to come in here? And that is the crucial question. And I mean, in theory, which, as Remy said, are coming from a theory group, and it's clearly that what you do is that you first use the standard potential, you make the Hartley-Fock model, get the overall picture, and you add the polarization, or what's called the electron correlation, as a perturbation. But if you take H minus, so I assume now here's a proton, and I have 1 electron here, surrounding here, and I come in with the second one. Well, Hartley-Fock model does not give you a stable system. You have to treat it as a 2-body system, a 3-body system. And what it requires is that the 2 electrons move in a correlated way. And of course, that's an extremely complicated thing if you have many electrons to include this. But here you have to start from including the correlation in the basic model to predict the properties. That's why and that's a key reason why we study negative ions, because if you have model negative ions, you are sure that that model also holds to model all other systems. So, and I mean, if I take this, what I said now, and put it into potential, the longer range potential seen here will then be the dipole, induced dipole potential, and the centrifugal barrier of the valence electron, which basically means that if this now corresponds to the 1 over R potential that you have in all other systems. If you have an S electron, then you have this potential decaying very rapidly. And then you have, for P or D electrons, you get this centrifugal barrier. Of course, as I said, it's extremely complicated to do the calculation in the proper way. On the other hand, if you look on this blue potential here, even for me as an experimentalist, I can say that's pretty much the potential we use in the 2nd or 3rd class in introductory quantum physics. And we can use this to show many different effects. And I will show you why this is the case. And what this means is that if I now look on an atomic system here, I have call it X and it, the ground state, excited state, and the Rydberg states and the photon. Well, for the negative ions, you will have basically maybe only one state, or maybe one more state. And then there's no Rydberg states, because that is a consequence of the 1 over R potential. You can have double excited states. So here you can say the potential is like more the square well, here it's 1 over R. And this gives them now very unique properties. So as I said, electron correlation is very important. You get a very small binding energy, about 1 eV, which we can use. There is few unexcited states, and almost no excited states with opposite parity. There's only 4 cases where we have observed an excited state with opposite parity, where you can drive, allow transition, and use it for detection. And yeah, so that is kind of the properties of them. I say, so why should we study them? And then, okay, I would say, benchmarking for electron correlation is the main reason why I came into this, coming from atomic physics. But it's actually very important in plasmas. Because in any plasma, you have the negative ions. I mean, if we charge plasma, and particularly in astrophysics, it's a lot of them, although it was only like 15 years ago, the first negative ion was detected in the stellar media. It's very important in accelerator mass spectrometry. That's the method used in carbon photon dating. It's used in heating thermonuclear reactors, the fusion reactors, where you see the person here, where you basically should fuse this ITER reactor that they're building in counter-reaction. And at CERN, they have a scheme to use this for sympathetic cooling of antiprotons. So there are many things, important fields where they come in. And then I will start what I do when I teach, coming back to my teaching role here. If I ask students, why is the sun yellow? Of course, when I teach their thermodynamics class, well, they say that because the Planck's distribution with 5,700 Kelvin give you a maximum, giving like yellowish color. And they all agree on this. Then you come to the nuclear physics class, and they say, what temperature you need to drive the fusion process? Well, then you need 100 million Kelvin. So why don't we see a black body scheme of 100 million Kelvin? Because that's the temperature of the sun in order to run the nuclear reaction. And the simple explanation of that lies in the negative ions. If I now take H and H minus, I put them, and this is in real scale. H minus binds and have an affinity of half an eV, which means that any wavelength larger than 2000, shorter than 2000 nanometer, will photodetach H minus. And in the solar atmosphere, you have everything from the sun. I mean, this is known for Fraunhofer, but mainly you have H minus, electrons, helium. But if I now put visible light onto this, well, this is the photodetachment cross-section curve for H minus. And I can see that it's very large cross-sections. So the solar atmosphere, the H minus in the solar atmosphere, will absorb all the visible radiation coming from below. Whereas if I look here for, and this is what there's a molecule, then the visible spectrum is here because you don't reach up. So that it would have been transparent. So what happened is that all the black body radiation for the very hot sun is absorbed in the outer layers of the atmosphere of the sun. And then there they rethermalize and submit again. So that means that it's the 5,700 Kelvin is the outer part of the solar atmosphere where H minus exists. So if it wasn't for H minus, so it wasn't for negative ions, I would not be standing here because life could not live on the Earth. That's the simple, yeah. most likely the density of that is, so this is kind of dominating. Yeah. Yeah. And of course, this is a very complicated thing that could be giving us a lecture or a research project. But actually, this was the first time negative ions and photodetachment process was described by Wilk in 1941. Okay, so what I do now in Gothenburg, I want to tell you a little bit. So this is the facility we have. It's called Gunilla. It's a small ion beam machine. And then we have a number of lasers. And then we call the photon factory of Gothenburg. And basically, we can produce atomic and many small molecular ions. We have a lot of different lasers covering huge wavelength ranges. We can use cross or collinear beams, and we can basically detect all products that is coming when we illuminate the negative ions with light. So now I will just show you first thing, what is a typical experiment, the standard experiment we can do. And assume that you want to measure phosphorus minus and measure how the binding energy of that. Well, what we do then, if I now look here on the energy level of phosphorus, it has three states. You have the ground state and three fine spectral components. And if I now apply light, I can then possibly detach them or not. So, and what we do then typically is that we detect the phosphorus atom. And basically what we do is that we have an ion source, we mass select, we bend the beam, and we bend the beam. And here we can see that we have a beam of ions. And then we apply the laser beam. And if this process occurs, the P minus has to be transferred to neutral. It will not be deflected. It will hit the glass plate. And the energy is like 6 keV. So the phosphorus atom will pin in the glass, emit an electron, and we detect that electron. So now we can then just tune the wavelength here. And then we see the following. So if I come with now increasing photon energy, below a certain level, there is nothing happening because now I cannot detach the highly excited state. At this point, this is when this state can reach the continuum and we neutralize them. And then as we increase it, we will first detach this, and this corresponding to the three threshold. And in this way, by determining, for instance, the point here, we can then determine the energy difference between P minus and P, which is the electron affinity. And I said the theory is very complicated, but this curve here was actually shown by Wigner that there's you can prove that if you have a breakup of a system, but there's no long-term interaction, you get a very simple expression, only a constant times the energy access to the power of the angular momentum of the outgoing electron plus 1/2. And in this case, it's an S electron that is emitted, so it's the E minus E to the 1/2. You can clearly see that this is square root behavior. You can easily fit and get this value. And this was done by Stephen Pontus Andersson quite some time ago. So with that, I introduced the field, and now I will pick 3 experiments to exemplify what we can do. And the first one I will tell you about is an experiment we did recently, and we studied an element called aspartame. And it's an element in the periodic table. Most of you have not heard about it. I had not heard about it before I was introduced to this, but if I put up the periodic table, it's there. It's the heaviest halogen. And the question is, why haven't you not heard about it? Well, it's the least abundant element on Earth. It's estimated 17 milligrams in the crust of the Earth, not per ton or per cubic kilometer. The total amount in the crust of the Earth is 70 milligrams. And the reason for this is that astatine is one of the decay chains from uranium. And the isotope of astatine that it passes has a lifetime of 1 second. So by looking on the mother isotope and how much we have of that, and the lifetime, you can make an estimate. And it decays through alpha decay to bismuth. But basically, before we started this, nothing about its chemical or physical properties was known. Even if there's nothing was known about it, it was actually used in an application. And the application is called targeted alpha therapy. And this is a cancer therapy that you basically use to treat the metastasis. I mean, I've learned a lot about cancer working with this now. I mean, if you get patient with cancer, you have a tumor, the surgeon takes the knife and takes out the tumor, but then you have the metastasis that are spread. And the typical thing is to give, I mean, this chemotherapy, basically trying to kill all the cells, but it also kills a lot of the cells in the body, and the patient is feeling very, very bad. This is a way you take an antibody that has to be designed to attach to cancer cells. And then you attach the astatine on the antibody, inject it in the patient, and this antibody diffuses around until it gets stuck on a cancer cell. And if it gets stuck on the cancer cell before it decays, then it can decay about 50% into the cancer cell and 50% out. And the good thing here with the specific isotope, I mean, there's hundreds of isotopes, but with this specific isotope is that the lifetime of this one, astatine 211, it's 12 hours, which means that it's good enough time for it to find its way before it decays. And the daughter is bismuth, which is not radioactive and not poisonous, not toxic. And of course, it will be very bad if it decays to another chemical element that goes around and do something other bad in the body. So it's like the ideal case. And also the energy of this alpha is typically so that the transfer time to stop, the stopping length is 1 cell. So the whole energy is dumped in the cell close to it when it decays. So we wanted to start, and I was in contact by a researcher, Sebastian Rother from CERN, who wanted to tell me about, said I had studied the ionization potential, and he wanted to study the basic properties of negative ion of the astatine. And if I now take the electron affinity of astatine, and just plot it here, and you see these are the affinities of the halogens. And when we started, this is the theoretical predictions with scanning from 1 to 3 eV, showing the difficulty. So the question is, what is it? And to measure this, it took about 6 years to do. And because this doesn't, we cannot have it, we produced it at CERN at a facility called ISOLDE. This is a big CERN complex. The big ring is used for this, the famous Higgs particles, but we can use the same proton beam. And basically what we do is that we take the proton beam, shoot it through a tube of uranium carbide. When it's shot through, it splashes the uranium molecules, nuclei, to absolutely everything. And you have spallation, fusion, fragments, whatever. You get everything. So basically you produce the whole nuclear structure here. Every isotope that exists is produced here. You extract it, you heat this to 2000 Celsius, you extract it into an ion source, make an ion beam, make a mass selection, and they can deliver astatine 211 to us. And then we built a detector there, it's called Gandalf. So basically we take the astatine, we bend it, as I showed you before, and we detect. The small technical difficulty is that the signal, the density in this range was about 0.01, which means that basically only 1% of the time we had one ion in the interaction region. At the same time, we have to pass the laser field through, and each pulse contains about 10 to the 14 photons, and they hit the target plate. And we have to avoid that they give the signal, and we can have a photoelectric effect making the ions. But nevertheless, we managed to scan the laser and found the threshold to determine the electron affinity. And we got this value. We were in contact with the leading theoretician, Anastasia Posevsky, and she calculated this to this value. And actually, I'll tell you the story. Those two was done by my students and her postdoc. They were invited to a conference. They had the result ready, the back-to-back conference. They were not allowed to communicate before, so they went up on stage. And first, my students showed this value, and then the theoretician showed this value. And this was later published, and then Rother had published the ionization potential, and just in short, if you take the ionization potential plus the electron affinity and divide by 2, you get the electronegativity. And that is the value that chemists are using to describe how does this element form a chemical bond binding? If the difference is 0, you get a covalent bond. If they're very different, you get ionic bond. So we can supply the most important value to chemists. And that means that we filled in this point in the Venn diagram of the ion. Okay, that was one experiment. Second experiment I will tell you about is about affinity measurement of O minus. And I just will very quickly show that. And this is actually, we made the most precise measurement ever made on an affinity. Here is an oxygen. And the problem with this measurement, as I showed you before, is that if you have an excited state, you get the background. So if you want to measure the energy difference from the ground state to ground state, that is actually that transition you here, but then you have a background below the threshold. And to study this, what we did was that we went to a facility called Desiree, which is a facility in Stockholm, where you can store ions in a ring at the pressure of 10 to the minus 14 millibar and at 13 Kelvin, which means that we can inject the ions and we can go take a coffee and come back and the ions are still circulating in the ring. So what we did was, and this is during the construction phase of this, it took about 10 years to design this ring. What we do is very simple. We inject the ions in the ring. So instead of dumping the ions, we study the same ions. Then by applying a laser here, A, that has the possibility that it detaches the excited state, but not the ground state. Leave that on for a minute. That means that we destroy all the excited states here, and we have a pure ground state beam. And then we had a kind of complex experimental scheme. And then we can do the scanning, as you saw before, but I should say here. Here, if you look here on the signal to background here, we have like 100 background and about 10 in signal. If we now deplete the excited state before, we come to this, and then we have about 10 in background and 100 in signal. So instead of 1 to 0, 10, we have 10 to 1 in signal to background. And we measured this, and it was a very long story. And one thing is the ions fly, and when you put the laser on, you get a very large Doppler shift. But if you first do it in this way, and then in this way, and then you take the geometrical mean, you can cancel the Doppler shift to all orders. And then we made a lot of experiments, and then this is actually the value that we got. And these are the previous experimental values that are certain years. So this was published in Nature Communication and as the most precise electron affinity measurement ever made. Sorry? No? I just tell you that tree there. Yeah. Okay. Why should you bother to study these numbers? And I'll show you the experiment we're working on now, because we're now looking into what's called the isotope shift. It contains a lot of information. And we can learn about the nuclear structure on this. So basically, it's to measure the difference between oxygen 16 and 18. And of course, and then you get the shift, which is a very important value in nuclear physics. But if you measure this, you can see that these are the values we got for 16 and 18. And you see they are very similar. So the difference comes up in the 6 digits, which means that you really need to have this high precision to see this. And this is something we are proceeding with. Okay, that would come to my final experiments. And now we'll just make a showcase of what we can use these ions because they have the special properties. And the element we study here is carbon. So we make a beam of carbon minus. Carbon, and if you look, and then we photodetach carbon and into the ground state of the carbon minus into carbon. When we do this photodetachment, we do it now with femtosecond lasers. They have very short time, which means that they have a very wide spectral range, which is wider than those 3 states. So if we do this photodetachment, we use a superposition here. And here we make use of the first effect that this is a pure state. It's a single state. So we have all the atoms in the same state, and we can then go into superposition of 3 states. And it's a T3 configuration. So you have the n equals -1, 0, and +1. And if you look on the configuration, the geometrical configuration of those, you have them here. Then it's been shown that if you use a high short laser pulse, you have much higher probability of detaching this with m equals 0. Which basically means that we produce a superposition of the ion where we get a donut-shaped wave function. And that, but now if you do this, it consists of those three states, but they have different energy, so the time of evolution will be different, which means that after some time, they will look like this. And now we take a second laser and photoionize this thing. And now if you photoionize it, when you are in this situation, you have no population along the z-axis, so nothing will happen. But so basically what we do is that we take a beam of negative ions, we take the laser beam. First we photodetach with one laser, we take a second laser and photoionize, and then we pull them to the detector, is a VMI, and measure them. And we see the following. If we take them at the same time, we get this. And this is basically, so basically you can say here, if you go out, this means 0 energy, and if you go out, it's higher energy. This is the photodetachment signal. But now if we wait a little bit, then we see the following. We see when we call jets, we see that ionization starts. And later we come to this, we can see a lot of ionization. And if you simulate this, you can say that what I show you here is the calculated structure of the ground state as time of after the time we created it. And I will now start the other one. We basically probe the population along the z-axis. This is experimental, yeah. So basically, we have repeated it by taking first one image with the first at the same time, and then delay the second pulse later and later and later. And you can see the clock. This was a 5,000, so it's 5 picoseconds. This experiment was done by students, and he was when he presented this, he was invited to a conference to present his results. And then he said, when he showed the video, he said, well, you saw that was my video. It was 5 nanosecond long, no, 5 picosecond long. It took me 3 years to shoot this movie. So I show it once more. So I do the same thing here. And just to discuss this, I think this is very much, I mean, this is nothing new, but I think it's very visualizing things. And when we have high school kids, they come to us, they have learned the Bohr model, they have the planetary thing. And then we tell the student, no, that's wrong. You have to see this as a probability distribution, as a cloud that is static. And the students are all right with that. And when I'm sure that they know that, then I show you this video to show you that we actually can manipulate the wave, the electron cloud around them. If you don't have a single state, but you have it in a discrete state. And the reason we can do this is simply that we have the initial state. We can use a simple femtosecond laser of 800 nanometers to do this photoionization. Okay. I think I skipped over this part and they just concluded. And basically, I hope I've shown you that we can actually use the negative ions to benchmark electron correlation. There are model systems for fundamental processes, and there are many important applications. And just to round off, coming back to the question here, are they good for you or not? But I show you, they're very difficult to detect. So nobody had really been able to test this. So the answer is we don't know. But I know, if you ask me, yes, they've been very good for me in my scientific career. And then I'll say what I wanted to finish off now, a little bit off the talk. This pilot program was terminated due to political reasons, due to war in Ukraine, but the Swedish government redirected the money. We have managed to find another source, which is called Erasmus+. So we have now two, well, it's not here, we have 2 positions, fully financed master project years for next year, that a student interested can do work on any of the different topics. And I have 2 PhD positions opening right now that the ad is out. The deadline to apply is 5th of March. And that is in the field of negative ions. And we're also working on something called a double degree scheme that is not yet finalized, but we hope that the administration will work through so we can start that, where you can basically make it master or PhD as a combined with two universities. And if you're interested in this, please remain afterwards, and I'm happy to ask questions about this, or you can mail me, or you can talk to Revi. And just to say what this topic of the PhD positions is that in this ring, it's actually a double ring. So we actually can inject negative ions in one ring and positive ions in the other ring. And if I inject negative ions here and positive here, in the mid region, they will fly with the same velocity. And we can study a process called neutron neutralization. So basically, if you have sodium in one and silicon in one, you can make the electron jump over, and we can detect it on a detector. And this is a very important process in astrophysics. So it's called laboratory astrophysics. And what I'm doing here is basically just to show you here that in this case, just what this is one of the projects is about. If you have excited states and make the collisions, that means that you don't know which state the atom is in. And the project is to manipulate this to try to form the ions into a certain state so we can see them and work on this. So that is the topic of this, one of the positions. And with that, I acknowledge the people that have done the work. And these are the students that have been the main contributors of the work presented. I'm very happy to see that if you see that it's very good gender balance in the group. And I thank you for your attention.
Hello. Thank you. It was very, very interesting. We open the session to questions.
Thank you for the very nice talk. I just have a quick question. Why is the short pulse more efficient and interacting with the electron field?
Why you get this directional? Basically, what we have the short field, which basically means that we make a multi-photon process. And basically, if you absorb one photon, you get the standard lobes of the P wave. If you have two photons, you get P wave squared. And here we came up to like 40 electrons. So you get and then if you make the lobe of the P wave and to the high power, it shrinks and becomes very narrow.
Yes, Luis.
Do you know about the industrial process to produce these TA units, the drug that it's used?
Yes, I know. Yes, very much. So the TA that is made, and I mean the very strange thing is I came into the project by meeting Sebastian Roth at a conference, and then that brought me to CERN, where I now have a big research group project running. And when he told me about this process, I Googled and found that the leading group globally was working 1 kilometer away from me in the University Hospital in Sweden, in Gothenburg. And what they do is that they go to in Copenhagen, where they have an alpha accelerator, and then they make a foil or bismuth, which is the K product, and then make the reverse process. So then take alpha particles and shoot into the film of bismuth, and then on the film you produce the astatine. And it's kind of interesting. What they do then, they run there for, maybe they get a beam time of 12 hours. They run and get accumulated. Copenhagen is only 2.5 hour drive from Gothenburg, so they actually put it in a taxi. They cut it up in lead, put it, and a taxi goes, because door from door is the fastest way, coming to the hospital in Gothenburg. And of course, then they have lost already 20% of the ions on the transport. And the whole point was that you have this astatine on a slide, and you have, I don't know this, but I mean, you have test tube with antibodies. I mean, how do you get the astatine to attach? And you have to kind of some solvent to get this out of that, and then you attach it to this, and you have to find a chemical process that, as fast as possible, and with the smallest loss, is producing this. And that is the point, that if we can supply them more about what is the chemical structure of these, they can then model better the most efficient path to use this.
Is there any other question? For you?
Yes. Isotope shift.
Yes,
You can see the very last digits are the difference.
yes.
So for example, I don't know, just thinking about stray magnetic fields, Stark effect, or I said, which effects do you have to narrow down in order to start telling apart?
You
It's
you see
different.
the isotope shift, the Stark shift is very small, and we do it in a field-free region, and we have very small magnetic fields. So if you put it in a very strong magnetic field, then the Zeeman effect would dominate over the isotope shift. But otherwise, in a field-free region, that's not a big problem. No, not at all. And I mean, basically, so the whole point there is that if you take the isotope shift, if you have the two electrons, then the electrons will circulate around. I mean, the isotope shift, you have the mass shift because the nucleus is not infinitely heavy, which means that when the electron goes around, it shakes with it. But if it's highly correlated and the two electrons are on opposite side and move like this, then it cancels. So that means that by measuring this shift, you can see how much is correlated. So it's a probe of the same thing. So we say that negative ions are highly correlated systems. The mass shift is a correlation effect. It's the ideal place to test correlation. And the other thing that happens is that the electron, when you have the potential for the electron, you have the 1/r potential, but then when it comes to the nucleus, it bends in. And of course, if you now add neutrons, then you change the potential. So that is a means to measure the R squared. So basically, so we do atomic physics study isotope shift, but the result will basically be the mean radius of the nucleus, which is a very important factor in nuclear physics. Because in nuclear physics, if you have a nucleus that is a sphere, but if you add neutrons, at a closed shell, it's a sphere, but if you add neutrons, you get an elongated, and when that rotates and tumbles, you get an effective larger radius. By measuring the R squared, which would be by isotope shift, you can see the deformation of the nucleus.
Any other question?
Yes, we can get my presentation.
I have a
But you cannot.
I have a quick question.
Yeah.
You mentioned the whole carbon-14 data method space to
Yes.
negative hours.
Yes.
And that means that nitrogen does not produce negative ions.
Yeah.
I don't know why, but you know why?
So I can say a little bit about what you said first. So carbon-14 dating, I think everybody knows about. You take Libby in the 40s, took a piece of wood from a fire from an Asian, and then you took a Geiger meter and measured the beta decay of carbon-14. And then you can see that the older it was, the less carbon-14 was left. So that was very nice. But if you just look on the decay of the carbon-14, then you have to wait because the lifetime is 5,000 years. So if you have a chunk of this and you measure it, you need a big log and measure for quite some time to do this. And also you have to dissolve it. So for instance, it has been used to date ancient paintings to say, is this a Rembrandt or is it a modern fake? But then of course, basically that method required the whole painting to be chemically dissolved and put in the machine to measure. And then you say, yes, it was real. Yeah. So, but instead with the carbon-14 dating, you take instead a sample, then you put it in an ion source, and then you measure the number of carbon-14 and carbon-12 ions. But the big problem is that if you do that, if you take positive ions and do that, you will get a lot of signal of mass 14, which is nitrogen. And then in the 70s, they can realize that N- does not exist. So the correlation is too weak. So N- cannot form. If you start by making a beam of negative ions, then you get rid of the background of nitrogen. And now you can instead take a hair of a fiber and that's enough. to make it dated. And nobody is, I can say, there's no clear thing, but I mean, all the negative ions are on the verge being bound, and nitrogen just happened that the correlation was not good enough to form.
Okay, no further questions? Then let's take Professor Dag Hanstorp all the way from sitting to here to talk about negative ions. Thank you very much. I encourage the ones who are interested in applying for the PhD position, talk to him. Yes. So please. Okay. Thank you, Doug.